Okay, this is part 2 of our video on section 3.9. Here are some applications of the use of differentials. The radius of a circle is measured to be 4.8 centimeters. So I have a circle, and I used a ruler, and I measured it to be 4.8 centimeters. But imagine if you're using some kind of a ruler or something, your measurement's not usually exact. You're kind of estimating that looks like about 4.8. So we're told that we have a possible error of plus or minus 0.1 centimeters. We could be off by a little bit. Now the question is, if we're off by a little bit in that radius measurement, would we be off in our circumference measurement? Well, sure, because any error in that radius is going to impact our computation for circumference. So we want to use differentials to find the possible error in the measurement of the circumference. Okay, so our function is circumference equals 2 pi r. We're going to get the differential form of this. Now, normally if I took the derivative of c, it would be with respect to r. So it would be dc dr. And that would just simply be 2 pi because 2 pi is a constant and the derivative of r is 1. In differential form, that would be dc equals 2 pi dr. Now dc is what I'm looking for because it's the error or the difference or the change in the circumference. dr is the amount of error or change in the radius. And what am I told that that is? Plus or minus 0.1 of a centimeter. So then dc, the error in the circumference, would be equal to 2 times pi times plus or minus 0.1 centimeters. Or in other words, would be plus or minus 0.2 pi centimeters. That's the approximate amount that my circumference could be off by based on the fact that I could be off in my radius measurement by plus or minus 0.1 centimeters. Similarly, we could find the possible error in the area. So area is pi r squared. The differential form for the derivative would be dA equals 2 pi r dr. I just multiplied the dr to this other side. So dA would be 2 pi. Now what was the radius measurement? Well, I thought it was 4.8. But was there an amount of error? Sure, plus or minus 0.1 of a centimeter. And this was 4.8 centimeters. So if I multiply that together, so I've got my calculator out, 2 times 4.8 times 0.1, and I get plus or minus 0.96 pi centimeters squared. That's how much my area measurement could be off by. Okay, but sometimes what I want to know is what percent error. Because if you have something that, say, has a value of 100 and it's off by 1, then it's only off by, say, 1%. But if you have something with a value of 2 and it's off by 1, then it's off by 50%. Could be a huge difference. So it's also sometimes referred to as the relative error because it's a way of describing how important this error is, to describe it as a percent or in relative terms. To find a percent error, you're going to take the amount of error, which was our dA, divided by the actual area measurement. So our error in area measurement was plus or minus 0.96 pi centimeters squared. The actual area, if the radius is 4.8, if the radius actually is 4.8, then the actual area is pi r squared. So the actual area would be 4.8 squared times pi, which is 23.04 pi centimeters squared. Okay, I'm now going to divide these two to turn this into a percent. The pi's cancel, so 0.96 divided by 23.04 gives me 0.0416 repeating. So as a percent, move the decimal 2 places, it's approximately a 4% error. Not exactly 4.16 repeating, but it does, well, it doesn't say approximate. Usually I put the word approximate on here. Okay, so relatively speaking, not a huge amount of error. You know, like in the polls you see, they always talk about a margin of error in the polls. That's the kind of thing we're talking about. Okay, if the radius is measured to be 4.8, what is the maximum allowable error in the measurement of the radius? That's of the radius. If the error in computing the area cannot exceed 5%. Okay, so I know if it's off by plus or minus 0.1, we can be off by 4%. But suppose I say, well, you know what? I'm okay even being off by as much as 5%. Well, how much could I have in terms of error in the measurement of the radius if I can be off by 5%. So we're going to work our way backwards. I know the percent error, again, is dA over A. But this time I don't know what dA is because I want to find out how much error I could have. The area is still 23.04 pi. I want that error to be no more than, so I'll go ahead and say equal to 5%, which is 0.05. Okay, from this equation, I'm going to solve for dA. So dA, if you multiply 23.04 times 0.05, you get 1.152 pi. So that's dA. But if I look up above, the relationship is that dA is 2 pi r dr. So now if I know that dA is 1.152 pi, that equals 2 pi r, remember, was 4.8, and dr is what I'm now going to find out. How much error can I have in the radius? Okay, take that equation and solve for dr. Okay, so you're going to take 1.152, divide by the 2, and divide by the 4.8. The pi's are going to cancel out, and I get that dr is 0.12. So that means I can have an error of plus or minus 0.12 centimeters. That's the maximum allowable error in the radius measurement, so that the error in computing the area will not exceed 5%. Okay, let's try another problem. Similar. A machine is designed to manufacture ball bearings. Those are spherical. So I'll sketch myself a little sphere here. And so a sphere has a radius with a radius of 0.8 inches. So my radius is measured to be 0.8 inches, but there's some error. The error is the differential for the radius, which is plus or minus 0.05 of an inch. Use differentials to estimate the range of volumes possible for a ball bearing manufactured by this machine. See, if there's an error in the radius, then there's an error in the volume, and I want to know kind of what's the largest possible volume and what's the smallest possible volume. Okay, the volume of a sphere is 4/3 pi r cubed. I'm sure you remembered that. So I take the derivative of this in differential form. That's dv, okay, equals, if I bring down the 3, it will cancel with the 4/3. I'll get 4 pi r squared dr. So dv is 4 pi 0.8 squared plus or minus 0.05. Okay, I'm going to multiply that out. So 4 times 0.8 squared times 0.05, and I get plus or minus 0.128 pi. Now, if the radius actually was 0.8, what would the volume be? Okay, let's see. If the radius is actually 0.8, then I'll take 0.8 cubed, and I'll multiply it by 4/3, and what I get is about 0.6826 repeating pi. Okay, that means my volume is this plus or minus the 0.128 pi. So my range of possible volumes is this. It can be as much as this plus 0.128, which ends up being 0.8106 repeating pi, or it could be this minus the 0.128. So the 0.6826 repeating minus the 0.128 comes out to be about 0.5546 repeating pi. So this is the range of possible values for my volume measurement. Okay, this last page is simply to practice a review. It has nothing to do with today's lesson. I just want you to practice taking derivatives. I want you to practice chain rule. I want you to practice quotient rule. I want you to practice product rule. It's really important that we have those basic skills down. So go back and review again the notes that we've taken on our new topic differentials. Try the homework on that new topic differentials, and also try these review problems, okay? The solutions to these review problems are in the solution guide to these notes that I will email you separately Friday afternoon. I don't want to email them to you before you try them in class on Friday. All right? Hope that goes well and that you understand this new topic.